Gonna turn on record. Okay, thanks for the reminder, Vicky. And we get a fresh page here. Well, maybe I can just undo this. Oops. Yeah, that works. I'm just curious about something. Let me just give something a try here. Oh, well, it was supposed to be back up at 5 p.m., but as I suspected, yeah, they don't have a great history, ICIT, in keeping this stuff going. All right, yeah, exactly, wishful thinking. Now, however, I did back up the entire course and the grades, the submissions and grades and stuff like that so far. So I know I know we're not going to lose any information and stuff like that, no matter what they do. The only thing I didn't do is I didn't think of it as to actually record everybody's email address. So I could get in touch with you guys without going through Blackboard. There may be another way for me to do that through the roster. If it goes on for another day, we may have to fall back onto that. Okay, so let's get started. Let me get this out of the way. Okay, so we started talking about we've last couple of weeks we've been talking about hypothesis testing. We started with the idea of confidence intervals and how we could learn about the way that repeated samples from population, when we took the mean sample size, would determine how variable that the results would be. And if we created a new distribution of just sample means, what that would look like compared to what the population looks like. So then we took that a step further. We started talking about using that to prove that there's a difference between one population and another population. In other words, if we take a sample from this population, find its mean, and a sample from this population and find its mean, well, now we have two means, one for this population, one for another. We don't know the population means, so we can't say definitively for sure that those two means are different. But we can say that if they're far enough apart and we understand the variability, well, how likely it is that we would get that big a difference in the means of the samples, we can say with some amount of certainty that those two groups have different means, those two populations have different means. And we can say it with a known level of certainty, right? We can say that that there's less than 5% chance that those means are the same in the two populations, less than 1% chance, and so on and so forth. So we can define what our level of confidence is when we talk about the differences between two populations. Okay, of course, we're all dealing. All this we were talking about now was all dealing with numerical variables, average variables that have an average, a standard deviation, and so on. Not necessarily nominal variables like ethnicity and so on. But that's going to come. We're going to get tie in with that pretty quickly. Okay, so we got another person logged in too now. Okay, good. So let's take a look at this from the. I'm going to go back over an example that I started before. I think I talked to you about this particular one. I'm going to make up a background for this rather than pull up a Word document or something like that. I'm going to make up a background for this particular sample. There's nine numbers here. I'm going to say that these 9 numbers represent, let me make it something pretty outlandish, the number of cases reported in a week by 9 different clinics in an African country A. And I know that African country B, make that an A. I know that in African country B, we were able to survey all of the clinics in country B, and we know that on the average that their clinics had, I'm going to make up a number here, their clinics had 8 cases on the average for all of their clinics. So this represents the population average, right? We were able to sample all the clinics in country B, but we're only able to sample a small group of the clinics in country A, whatever reason, accessibility or economic considerations. We can only serve a these 9 randomly selected clinics. Okay, so if we want to compare country A to country B, remember, this is a population, right? We want to compare country A to country B. Well, we need to know the average of this sample. Right, let's get the average of this sample. Okay, and it comes out to 9.888. I'm going to make that red. So this is the average number of cases per clinic in this country based on a sample. This is based on an actual count of the entire population. Okay, so now let's say to ourselves, well, I don't know what the variability is here now. I know the mean for this population, but I don't know what the variability is in terms of how likely is it that this particular result is really close to the true population average for all the clinics for country A. So I need to get a handle on the variability for this sample. So I'm going to take the standard deviation. Okay, so the standard deviation turns out to be 2.93, roughly 3, let's say. Okay, I'm going to give that another color. Okay, so that's our standard deviation of the population of the sample that I have here. So now I don't know the standard deviation of the entire population. I only know the standard deviation of the sample. Okay, well, I'm going to take that sample. I'm going to, okay, let me just label these: standard deviation, mean, and also going to put sample size down here. Sample size is 9. Okay, and I'm going to say to myself, okay, here's the result that I have here, but I know I can create a confidence interval for this mean, right? Now, how would I create a confidence interval for this mean? The way that I would create a confidence interval for this mean is I would say to myself, okay, let's find out if I can generate a margin of error that I can add and subtract to this mean that will represent the variability of taking this sample over and over again. Okay, so I'm going to do that. First thing I need to do is calculate a standard error. Okay, what's the standard error going to be equal to? It's going to be equal to the standard deviation of the population, sigma. We don't have that, so we got to use this, divided by the square root of the sample size. Now, I'm not going to use square root because I can see it's 9, and I know square root of 9 is 3. So the standard error is a little under 1. So now I want to generate my confidence interval. Okay, what's my confidence interval going to be equal to? My confidence interval is going to be equal to x, the mean of the sample, plus or minus my margin of error, right? What's my margin of error equal to? That's x bar plus or minus. Okay, so now I'm going to put in a z-score here. If I know the population standard deviation, I would put in a z-score. Since I don't know the population standard deviation, I'm going to put in a t-score. And that t-score is going to be t-score for alpha is equal to 0.05. Whatever that value happens to be. It's going to be a different value depending on the sample size. We have to go to the t-table to look up and see what it is. Plus or minus the t-score that I need for a 5% alpha, okay, times my standard error. Okay, so let's look up what that t-score is going to be. Got a folder up here that has that, I think. Okay, t-scores. Here we go. Gressney and Franklin is another textbook that we used to use years ago, and it had pretty good tables in it. Okay, so now I know that it's based on my sample size, which is 9, but the t-table uses degrees of freedom. The degrees of freedom in this case is 9 minus 1 or 8. So 8, and if I want 95% certainty and 95% confidence interval, or in other words, 5% in each total of 5% total, that could be in either tail, 2.5% in one tail, 2.5% in the other tail. In other words, on either 2.5% error on either side of the mean for a total of 5% error, or in other words, 95% confidence. This is the column I would be using. So the t-value I'm going to use is 2.306. I'm just going to use 2.3 for now to make it a little easier. So my confidence interval, oops, I didn't mean to do that. Did I? Oh no, redo. Okay, but I'm going to just redo this. My confidence interval is going to be equal to, let's see, my standard error, I got that. So my t-score, my critical t is going to be 2.3. I'll use this, I'll make through the whole thing. Why not? We're using a computer to calculate this. So now I'm going to do my actual calculation. So it's going to be equal to the one side, it's going to be equal to the mean plus t times my standard error. Okay, it's going to be equal to 12.14. And on the other side, it's going to be equal to my mean, equals my mean minus t times my standard of error. So I'm 95% sure that the true mean for all the clinics in country A is between 7.6 and 12.1. Well, that means that it could be 8, right? I can't say with 95% certainty that it's not 8, right? Now, so that means I can't really say with the level of certainty that I've assigned myself, a 5% chance of being wrong, 95% confidence. With that level of certainty, I can't say that it's different than 8. Now, had in country B the average been 7, I would have been able to say, gee, there's less than 5% chance I would get that extreme an outcome, that these two means would be so different that that they would really be the same mean for both countries. Okay, so I'm going to pause there and ask you guys, are you comfortable with that? Does that make sense to you? Okay, anybody uncomfortable with that? So, because I'm about to put a little teeny tiny twist on it right now. Outside of the margin of error, right? Outside of that confidence interval. That's right. There's less than 5% chance that you would get a result that would be outside of that confidence interval for the true mean. If you took a sample, if you took repeated samples even. Okay, so now for 7, you'd be outside of the confidence interval. You would say, oh, we're 95% sure that these two countries have different averages for the countries. But at 8, we couldn't say that. So now I'm going to use 8. I'm going to use 7 for now. Okay, I'm going to do this a slightly different way. And the way I'm going to do it this time is I'm going to say to myself, how many standard errors apart are these two means? So how am I going to do that? I'm going to say, okay, I'm going to say standard error. Another way of saying standard error or standard deviation even. Remember before we used to say that the z-score is another way of saying how many standard deviations away from the mean you are. A z-score 2 means you're 2 standard deviations away from the mean. A z-score 3 means you're 3 standard deviations away. Same thing with a t-score, except with a t-score, we're dealing with situations where we don't know what the population standard deviation is. So we have to make accommodations for the actual level of uncertainty that we have. So right now, since I'm dealing with a sample, I'm going to call this number t. And I'm going to say that the number of standard errors apart that these two numbers, 9.88 and 7 are, is going to be equal to the difference between the two means. Minus 7, x bar minus mu, right, the mean for the population, over the standard error. In other words, the difference between these two divided by the standard error is the number of standard deviations apart that they are, standard errors apart that they are. So I'm going to go ahead and actually calculate that. So that's equal to x bar minus the known mean, 7, divided by the standard error, which was that. I'm going to hit enter. And the t-score that I get that's represented by that difference is 2.73. Now I'm going to go back to my t-table. When we have a sample of size 9, 8 degrees of freedom, our two means have to be, our sample mean and our mean that we're comparing it, have to be 2.3 standard errors apart in order for me to, at least 2.3 standard errors apart, in order for me to be sure that I'm 95% sure that I can say that they're different. Okay, I'm avoiding using terms for hypothesis testing, null hypothesis right for right now. But they have to be at least that far apart in order for me to be sure that I'm 95% sure the two means are different. If they're not that far apart, then I'm not 95% sure. Just like that means that they would be within the confidence interval of one or the other, right? So that's the number I'm going to use here. Now, what if I had used 8? If I had used 8, so I'm 95% sure that these two are different. Now, what if I had used 8? And if I had used 8, I would have gotten x bar minus 8 over the standard error. And our t-score, oops, I'm sorry, I made a mistake there, equals x bar minus 7, 8 rather, over the standard error. Okay, and I think I might have to do this to make this work. I think if I use the numbers instead of letters, and it comes out to be, that seems too small. X bar, what did I do here? Over 814. Oh, I'm sorry. I used to. You know what I did there. You guys know what I did there, right? I used the standard error. I used the standard deviation instead of the standard error. I kept saying standard error. I kept using standard deviation. Standard error. That number of standard errors apart, and that comes out to be 1.93. Now 1.93. No, you got it's standard error, not standard deviation, right? Because we're dealing with samples. Okay, so if I go back here and look at this again, what do I have to exceed in terms of the t-score in order to say that I'm 95% sure that they're different? I have to exceed 2.3. And in this case, when I made B8, then the two were not far enough apart, so my t-score was only 1.93. So I can't say that I'm 95% sure that they're different. Yes, standard error. This formula up here, yeah. Okay, so now we're gonna formalize this, right? What we've done here is very similar to what we did with the idea of calculating a confidence interval and seeing if the other mean is within the confidence interval. This is something called a t-test. When you do a t-test with a single sample and you compare it to a known mean, this is a one sample, it's called a one sample t-test. It's pretty much like the result you would get from a confidence interval. When you have two samples, if I had two columns of numbers and got two means and wanted to compare them, it gets more complicated. And as we move forward, you'll start to see why it gets more complicated. But before we go to that, we're gonna review some of the rules of hypothesis testing. Okay, so let me open this up. Here we go. Here's a slide from one of the presentations. Okay, so what do we do when we're doing hypothesis testing, when we're doing a t-test? The first thing we do is we state a hypothesis. We actually state two, a null hypothesis and an alternative hypothesis. Our null hypothesis always has an equality in it. In other words, we're starting from not knowing whether the two means are different from one another. We want to prove that they're different. That's almost always the direction you're going to be going, because generally you're going to want to prove that a drug worked. So you want to prove that the results of the drug are different than the results of the placebo. You want to make sure that you want to prove that a intervention worked. So you want to demonstrate that the performance of people that received training is different than the people that didn't receive training, for instance, that kind of intervention, right? So you're trying to prove a difference, but to prove a difference, you're going to start with the assumption that they're the same and then you're going to go through an exercise to prove that they're different. That's what hypothesis testing is all about. Okay, so we're going to state a hypothesis, no, and an alternative. No means just no difference or zero, right? So no hypothesis is going to be that the two means are the same. And the alternative hypothesis is what we want to prove, that they're different, that the two means are different from one another. We're going to specify a significance level. By a significance level, we're going to call that alpha. By a significance level, we're going to say the level of error that we're willing to accept. So, for instance, if I want to be 95% sure that I can justify rejecting my null hypothesis, saying they're not equal, and accepting my alternative hypothesis, instead saying that they're equal and accepting my alternative hypothesis. Let me rephrase that. If I want to be 95% sure when I reject my null hypothesis that the two means are equal and accept my alternative hypothesis that the two means are different, well, then that level is the level of error I'm willing to accept. Alpha is the level of error I'm willing to accept. 95% confidence means you're willing to accept a 5% chance of being wrong. 99% confidence, you're willing to accept a 1% chance of being wrong. 90% confidence, you're willing to accept alpha, 10% chance of being wrong. So that's our alpha. We have to choose that ahead of time. In other words, it's cheating a little bit to say, well, after I've done all this, I got to about 9%. Why don't I say my alpha is 10%? That way I can reject my null hypothesis. You really want to specify your level of significance that you're going to, for that particular analysis, that you're going to feel is acceptable. Most of the time, in most of the statistical studies that you look at, it's 5%. Okay, so we're going to draw samples from either one population or both populations. And we're going to compute a test statistic. That's that t-score, number of standard deviations apart. Okay, if the normal distribution, if we know the population standard deviation sigma, we can use the z-table to determine the probabilities. But most of the time, we're not going to know the whole population. So we're going to use the t-distribution, the t-score, instead, because we have to estimate the sigma using the standard deviation of the sample that we took. Okay, they get a little bit more complicated as we move forward when we get two samples. Which one of those standard deviations are used, but we're going to approach that. Then we're going to determine the p-value, or in other words, the probability that we're wrong. Really, we're going to determine two things: the t-value and the p-value. They link up together. A big t-score means that a large t means that it's lower probability. They're so far apart that it's a lower probability, a lower p-value, that they're the same and that you shouldn't reject your null hypothesis. A lower t-value means you have a higher p-value, a higher probability of being wrong if you say the two are different, right? And they match up with one another. In fact, the critical value of t for any sample size is a p-value of exactly 0.05, right? That's how these two things match up. Then we're going to compare p-value to the significance level alpha, and the probability of being wrong, if we reject the null hypothesis, we want that to be less than our acceptable level of probability alpha when we decide whether we're going to reject or not. Okay, if p-value is less than alpha, we reject. If p-value is greater than alpha, we fail to reject. Okay, same thing with the t-score. If the t-score is less than t-critical, we fail to reject, because that goes along with a high p-value. If the t-value is higher than t-critical for that sample size, then we reject the null hypothesis, because we know they're far apart, the two means, and the p-value is going to be smaller than 0.05. Right? Big t-value means a small p-value. A small t-value means a big p-value. In other words, a higher probability of being wrong if we reject them. Okay, so a little confusing, right? But not terrible. Okay, so let's put this to work. Okay, so in this particular case, this is a one sample t-test. I only have one sample. I'm comparing it to a known mean. My null hypothesis, right, My null hypothesis was that the mean for population A is equal to the mean for population B. And my alternative hypothesis was the mean for population A does not equal the mean for population B. Okay, so that's simple, right? So now I'm also going to say, well, my alpha equals 0.0.05. Oops, 5. Okay, 5. Okay, now my T critical, I have to look up. Okay, my T critical for a sample size of 9 and alpha equals 0.05. Okay, that's the same as a 95% confidence interval. Notice here it says 0.025, 2.5%, right? Not 5%. Well, that's only the amount that's in the right side of the curve. But remember, we could be that far away on this side, but we didn't say it could only be one mean could only be bigger than the other. It could also be smaller than the other. So when you see this 0.025, this right tail probability, that means 2.5% here and 2.5% here. So this is 5% chance of being wrong. 95% confidence, 5% chance of being wrong. And our critical value of T is 2.306. So our critical value of T equals 2.306. So now we can go ahead and do our t-test. And if our t-test comes up to be larger than our t-score, we reject our null hypothesis. We reject it because a t-score that's bigger than t-critical means that our p-value is less than 0.05. Right? Okay, and if our t-value did not exceed our critical value of t, if instead it had been 1.93, that would have meant our p-value was greater than 0.05. So we would have failed to reject. Now, remember now, we only set this equality up because we wanted to disprove it. We wanted to have the evidence to say this is not true, that this is true instead. Okay, so that's the way that we're going to work this. But now what that means is that if you fail to reject your null hypothesis, which is what your objective had been, that doesn't mean your null hypothesis is true. It only means that you didn't have the evidence to reject it and accept your alternative hypothesis. So we never say we accept if we fail, if our T critical is, if our T is smaller than T critical, or if our P is bigger than 0.05, we never say we accept the null hypothesis. We only say we failed to reject the null hypothesis. We failed to, say that we failed to prove that it was, that we could reject it at the level of confidence that we wanted. Okay, and that's basically what we're doing here. You have to state your null hypothesis and your alpha, and in this case, it wouldn't hurt to put T critical because we're going to need it anyway. Okay, so I'm going to do the same thing now with SPSS and see if we get the same result. By the way, these I emailed these to you guys, so I think most of you guys probably have these available to you. I have the same file in here. One sample t-test, one sample test. Should have put t-test, but you get the idea. Okay, put that away. Open data. Go to my desktop and it should be in here. Here's my one sample t-test. It's exactly the same data. Okay, here we go. Same 9 numbers, right? X. Okay, and actually thinks it's a categorical variable because they're small numbers, and it says, oh, maybe they represent ethnicities. Maybe there's 14 separate ethnicities. So I'm going to go in here and I'm going to make sure it knows that it's a scalar number. It's a numerical variable. Okay. I did that because it might not let me do the analysis that I want unless it knows that it's the right kind of variable for that kind of exercise. You would hope it would warn you about that anyway. Doesn't always. Okay, so now, as I do with most stuff, well, first thing I'm going to do is I'm going to verbally state my null hypothesis. My null hypothesis is that the mean of population X is different than the mean of Null hypothesis, the mean of population X is the same as population Y. My alternative hypothesis is the mean of population X is different than the mean of population Y. My acceptable level of error, alpha, is equal to 0.05. I want to be 95% certain, less than 5% chance of being wrong. So I'm going to go ahead and I'm going to do this analysis. As most analyses in SPSS, we start up and analyze. Analyze. Now we're comparing means of two groups, so I'm going to go in there. Now we know that there's only a single sample here, right? Independent samples refers to when we take two independent samples, one from one population, one from another. In this case, we're taking one sample from a population we don't know the mean of, and we're comparing it to another one that we do know the mean of, or we think we know the mean of. Okay, so I'm going to move the test variable that I'm working with in here, which is X. It was A over before. And I'm going to put the mean that I'm comparing it to over here. Okay, so for argument's sake, I'm going to put 7 in there. We got lucky with 7. So I'm going to use 7. Now in here, let me redo that so you can see it. In here, under options, I can tell it what level of certainty that I want. Options, okay, 95% certainty. I could change that to 99 if I wanted to, but I'm going to leave it 95. Okay, so our alpha is 0.05 because they left that at 95%. Okay, our test value is 7. So what happened when we used the 7 before? We were able to reject the null hypothesis. T was bigger than 2.03, and our p-value, we speculated because of how big T was, we speculated that P was going to be less than 0.05. SPSS will actually calculate that for us now. So I'm going to click OK. The output window comes up, and sure enough, here is our table. The mean of that population is 9.89, it rounded it. Standard deviation is 2.93, and the standard error of the mean, that standard deviation of the sample distribution of sample size 9, is 0.978, right? That's the one we're going to use to find our t-score. So let's calculate t-score. I calculated the t-score as being 2.953. I'm wondering, was that the same as we got? Oh, I got a different one. I'm not sure where I got. Oh, maybe one of these numbers is different. You know, sometimes they change the numbers for different exercises and stuff like that. 5, 7, 8, 9, 10, 11, 12, 13, 14. I'm not sure why. Not sure why it comes something different, but I'm not going to worry about that for now. Okay, so our t-score is 2.93, which is bigger than our critical value of t, right? Not 8 degrees of freedom. And the p-value, the probability that we would get that big a t-score if the two groups had the same mean is less than 2%. It's 0.018, right? So I can say, because the t-score is bigger than the critical value of t, and also because my p-value, my probability of being wrong if I reject the null hypothesis, is less than 5%, I can go ahead and reject the null hypothesis and say that the two groups are different. Okay, now I'm going to run it again for when we did it with 8. Where am I? Compare means, one sample t-test. Okay, hopefully it won't make a liar out of me. Okay, and here's our t-value now, 1.931. And our p-value, our probability of being wrong, because that's such a small t, is going to be 0.090. So I don't exceed my critical value of t, and my p-value is greater than 0.05, so I fail to reject my null hypothesis. How's that sound? You guys okay with that? Not that complicated, right? Most of the time, you are going to use SPSS in some. Well, excuse me. Let me qualify that. In the future, after you get out of this course, you'll always use SPSS or some similar tool to actually calculate this, right? For this course, we might tinker around a little bit. We're using Excel, especially on something simple that's like a single sample t-test. We might do that. Or when I demonstrate it to you, we might actually do that. The p-value, okay. The t-value means the number of standard errors apart that these two means are. In other words, these two means are roughly 2 standard errors apart, right? Let me go back here. When we were comparing it to 8, this is 10, this is 8. The difference between the two means is 8. The standard error is about 1. So the number of standard errors apart that they are is 2, just like you might say two z-scores apart. So the likelihood that we would get these two things that far apart, if they were really the same mean in both populations, the likelihood of that occurring is about 9%. That's not good enough for me to say that they're different. Okay, the likelihood of them being from the same population has to be less than 5%. And the t-value describes to us what that likelihood is. So a t-value of 1.93 is not big enough, not far enough. These two means are not far enough apart for me to say that they're different from one another. Okay, in other words, reject the idea that they could possibly be from the same population, or they could actually have the same means. Okay, now 7 and 10 are 3 standard errors apart almost. So in that case, I have more evidence. I can say they're further apart. The probability of them being the same mean, really, if I had taken all the means of all the clinics in country A instead of just a sample, probability that I would have gotten the same mean based on this random sample is 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 quite likely for 7, but not likely for 8. At least not at a level that I can reject the null hypothesis. Okay, so what does that mean? That means when you have two means that are far apart, they're going to have a big t-score. When you have two means that are close together, they're going to have a small t-score. So a big t-score goes along with a small p-value. The p-value is the probability that you would get the same mean, that that big a difference would come from two groups that have the same mean. In other words, your null hypothesis. Okay, so you got a big t-value, you get a small p-value, means that you can reject your null hypothesis. When they're close together, your likelihood of being wrong if you say that they're different is a lot greater. It's going to be greater than 5%. So big T value, small P value. Small T value, big P value. And the T value we're most interested in is the critical value of T. The number for T that represents a 5% chance of being wrong if you reject the null hypothesis. So if we did an analysis and the t-value came up 2.73, we would reject the null hypothesis because we knew there's going to be less than 5% chance of being wrong because the critical value of t is 2.3. Okay, and we've exceeded that. If we calculate t-score and it's 1.93, we fail to reject the null hypothesis because we know that we didn't achieve the size t-value that we need for a 5% chance of being wrong. So since it's smaller than the critical value of t, the chances of being wrong, that p-score, is greater than 5%. So we can't reject the null hypothesis. Okay, so I don't want to beat this to get that too much, but that you'll get a feel for this as we continue to work with this stuff. Okay, now the interesting thing now is that now we're going to get into some real statistics, some real situations that you might wind up in, where you might actually do some measurements or a survey or an experiment where you actually want to go ahead and do this analysis. Okay, and in this case, I'm going to look at another situation. Okay, whoops, I didn't mean to open that one. Okay, this case, I'm going to look at two samples. This is a sample of males. This is a sample of females. And whatever these parameters represent, I want to know whether the average for the males is different from the average for females. Okay, now I'm not interested, again, this is a sample of 9 males and 9 females. I'm not interested in what the average for this sample is. I'm interested in knowing what the average for all the males in this population are. versus all the females in this population. But I'm never going to know that. So the only thing I'm going to know is what the average is for this sample and the average is for this sample. And whether, and from that, I have to determine what my level of confidence is if in terms of, can I say that they're really different? Okay, so how are we going to do that? Remember our steps we were going to go through. First, we're going to state our null and alternative hypothesis. Okay, my null hypothesis. Okay, the mean for males equal mean for females. Okay, good enough. What's my alternative hypothesis? Somebody state my alternative hypothesis for me. Somebody want to give an idea, an alternative hypothesis? Pretty obvious, right? That's exactly right. Just different, not equal. Mean for males does not equal mean for females. Okay, notice I use mu because mu, or as close as I could get on this computer to mu, mu, because I'm interested, when I would state my hypothesis, I'm interested in the mean for the populations, not for the samples. But I have to work with the samples. So what level of alpha do we want? What are we going to make? What are we going to set alpha equal to? Anybody want to? Yeah, 0.05, 5%. Good. Most of the time, that's what we're going to be happy with. Okay, so now let's go ahead and calculate our means for each one of these two groups. Okay, average for males. Okay, equals average for females. Okay, is that, actually tell you the truth, I'm not sure if this is a round number. Could be, right? 11.98. Yeah, it's round. This is exactly 10. Okay. I didn't know if what the formatting was there. It was hiding decimal places. Okay, so these are our two means. Now I have to calculate, in order to do my t-score, what's my t-score going to be equal to again? I got to figure out how far apart these two are in terms of standard errors, okay, for that sample size. Right, so my t-score is going to be equal to, it's going to be equal to x bar 1 minus x bar male minus x bar female over the standard error. What, x bar? That's interesting. Okay. So at any rate, I'm going to put parentheses in there just so we know what's happening there. Right? So that's going to be our t-score, the difference between those two divided by the standard error. I got a little bit of a problem here. That is that this one has one standard deviation. And the other one has a different standard deviation. Now, they look pretty different, don't they? But, you know, for our purposes, unless one is at least double the other one, we're going to say that they're roughly equal, these two standard deviations, reduced populations. So, in the absence of using this one or this one, we're actually going to pool the two of them and do a weighted average of the two of them and use that standard deviation to calculate the standard error. Okay, well, how am I going to do that? That sounds a little cumbersome. Well, I got a chart here that you're gonna use that should help you out with that. Let me see if I can't find it. Hope it's in here. Okay, that word's a little bit hinky here for me. I gotta wait for Word to kind of kick in here. For some reason, since I did the last update, it's very slow to open. Page comes up quick, but I actually can't do anything for about 10 or 15 seconds. Thank you, Mike. There we go. Suddenly seems to be coming to life. Okay, well, yeah, these are some examples. It's not the document I want. I thought I had given it to you. Steps. T-test vary. Here we go. It's this one. Okay, so I put together a kind of a chart for you guys. Okay, And that is when we're comparing the means of two populations using the t-test, right? Well, the one sample t-test is simple. We don't have to worry about that. There's only one standard deviation, one standard error. But now, when we have two populations and two samples, things get a little confusing. Now we need we have to make an assumption. First assumption is if the standard deviations of the two samples are equal, the two populations are equal. That's one assumption. The other assumption could be that the standard deviations are not equal. Well, for our initial purposes, for our playing around with Excel and stuff like that, we're going to say that if they are if one standard deviation is twice the other or more, then we're going to say they're not equal. We're going to assume them to be not equal. But if they're not twice the other, we're going to stick with that they're equal. Okay, so how am I going to calculate the standard deviation that I need to use? Well, what you're going to do is you're going to create a pooled standard deviation that's going to match this formula. I'm going to pull up Excel, and it's kind of a nasty formula. I know that, right? And most of the time you're not going to have to do this because we'll find other ways to deal with this. Mainly SPSS. That's a good question. Let's see if it comes out the same. It's kind of weighted, but let's see what. First of all, number one, you're not always going to have equal numbers in both groups, so you got that problem. Let's do this and see how it compares. Okay, let's do this little experiment. So I'm going to call this my pooled standard deviation. Okay, and it's going to be equal to the square root of n minus 1 times standard deviation 1 squared. So I'm going to do that first. N1 is 9 times, okay, let me put an equal sign in there, equals uh, 8, rather, n minus 1 is 8 times the standard deviation of group 1 squared. That's that times itself. Okay, that's going to be that first part of the top. Now the next one equals, that's going to be n2 minus 1, which again is 8, times the standard deviation of that group squared. Tell me if I'm doing something wrong here. Okay, and then on the bottom, the denominator is going to be equal to, it's going to be equal to n2 plus n1, which is 9 and 9, 18 minus 2 is going to be equal to 16. Okay, so my standard pooled standard deviation is going to be equal to this plus this divided by 16. And I'm going to take the square root of that whole thing. First, I'm going to put this in parentheses. Then I'm going to preface this with square root. Okay, so now I'm going to cross my cross my fingers and hope this works. Oh, did I do something wrong? N is 9, but it's asking for n minus 1. So I'm n minus 1 or n2 minus 1. Okay, so I'm going to hit enter. I'm going to cross my fingers, hit enter, and I get 0.593. Okay, so now we're not done yet. So my standard error, something seems wrong there. I got that right? Calculate pool standard deviation, 30, 30. That doesn't seem right to me. I think that I didn't bracket that correctly. I think what I got to do is I got to put parentheses around the whole thing. Get it to do the whole thing in a square root. That's better. Okay. My pooled standard deviation is 2.37. Is 2.37 the average of these two? Let's give it a try. Not quite. It's a little bit different, isn't it? Okay. Let's ignore that for now. But you get the idea that it's pretty close. And this would at least, help us deal with unequal. You really wouldn't want to just average them if you had a different size sample in each one of them. So let's stick with this. Let's stick with the one we just calculated for now. So my t-score now is going to be equal. Now my standard error, which is going to be the bottom of this equation, right, is going to be equal to my pooled standard deviation times the square root of 1 over n2, which is 1/9, 1 divided by 9, plus 1 divided by 9. Let me think if that's going to work out okay. It's going to do the division, then it's going to do the addition, then the square root, then the multiplication. I hope so. Okay, so my standard error is equal to 1.11. Okay, so now the bottom of my equation, oops, I didn't quite do that right, did I? That is, that's B18. Is that right? B18. Yes, it is. That seems right. Okay, so what's our t-score going to be equal to? Our t-score is going to be equal to, x bar 1, put parentheses in there, x bar 1 minus x bar 2, parentheses, over my standard error. So my t-score is 0.71. Now, I don't know if that's right or not. I'm going to use SPSS to check our work. First thing I need to know is what's the degrees of freedom, because that would indicate degrees of freedom, n plus 1, n1 plus n2 minus 2 is 16 degrees of freedom. So that means our t-score that we would have to exceed for 16 degrees of freedom, t-score that we would have to exceed is 2.12. And we don't exceed it if our t-score is indeed 0.71. Let me think about this for a second. Difference. Oh, you want to know something? I made a mistake here, didn't I? You guys got to catch me when I make these mistakes. Otherwise, I'll just keep on yapping away. Okay? I plugged in these two numbers instead of the mean. Yeah, I didn't label them, right? I really should label this stuff so I don't confuse me and you. 10, the mean for the first group minus the mean for the second group, divided by the standard error. And it's 2.18. T is 2.18. Okay, so now that we have 2.18, we have to compare that to our critical value of T, which for 16 degrees of freedom, remember degrees of freedom is equal to, we saw on this chart, degrees of freedom for this kind of analysis is going to be the sum of the two sample sizes minus 2. So that's 9 and 9 is 18, right? Less 2. Okay, so let me find my alpha. Okay, 16 degrees of freedom. My critical value of T is 2.12. Did I exceed my critical value of T? So you tell me, did I exceed my critical value of T? Yes. So do I reject my null hypothesis? Yes. Right? Everybody agree? Yes? Right. Reject and accept my alternative hypothesis. Now I know my p-value is going to be less than, since I exceeded the critical value of t, I know my p-value, probability of being wrong, is going to be less than 0.05. We're going to test that right now with SPSS, see if we get the same answer. How exciting is this? Isn't this great stuff? Okay. Okay, let's see. Open data. Okay, 2-sample t-test. Okay, and I'm going to go down here, male and female. I'm going to go to analyze, compare means, independent samples. This time it's independent samples t-test. And I'm going to move, let's see, the test variable is the values, the numbers, the things I'm going to find the numbers, the quantities of, the mean of, so on, standard deviation of. And the grouping variable is gender. I'm going to move that in there. Now it wants me to define the groups, and by define the groups, it wants me to tell it what number, what was actually typed in here for male and female. I think it's 1 and 2. If it's not 1 and 2, it's not going to do it. So I'm gonna fly without a net rather than go back and checking it. In options, I want to make sure 95% for 5% confidence interval. Okay, good for 95% confidence interval. Then I'm going to click OK, and let's see what comes up. See if I got lucky. It appears I got lucky. There were 9 females, 9 males, 10, 7.56, same numbers we got. Now calculate standard error for both of these two. And then you want to know something? I got a feeling maybe if you average the standard error, if it's equal sample size, you average standard error, you might actually get that to be the same. But let's see what we got. Okay, what we got was a t-score of 2.184. That's exactly the number that we got, right? So instead of giving us the critical value of t, SPSS has an infinite number of t-tables built into it. It can actually respond to us for 16 degrees of freedom. What's the exact probability of being wrong? And it's 0.044. And just as we did when we compared the t value we calculated to the critical value of t, now we can compare the p-value, the probability of getting that an extreme a difference, 2.148, 184 standard errors apart. We can compare that. The probability of that actually occurring is less than 5% of the time if the null hypothesis is true. So we have less than 5% chance of being wrong if we reject the null hypothesis. I want to show you one other thing that's going on in here in this table. Notice there were two lines there, right? And the two lines there are there because before SPSS, remember I mentioned that there's a separate way to do this. Here, I think you may not have mentioned it, but I started to show you as I scrolled through that page with the formulas. SPS, there's a separate procedure, separate set of formulas that we use. It's a different way of calculating degrees of freedom and the standard error and so on and so forth. When we assume when we're willing to assume that these two samples have the same standard deviation, versus if we want to say that they don't have the same standard deviation or variance, in other words. Okay, and what this does is SPSS actually does a test. It's called Levene's test for the equality of variances. Okay, and just like almost everything else you do in statistics, the first assumption is that the things are equal. Equal variance is assumed is the top line, right? And the bottom line represents the calculations for equal variances not assumed. So which of these two lines should we use? T-score came out the same. The p-value came out a little bit different. Which of the two lines here should we use? Well, this determines which one of those two we should use. We start with the assumption that the variances are equal. SPSS does this test. It calculates a test statistic, and it gives us a probability, a p-value. If our probability of being wrong, if we reject this, is 25%, 24.5%. That's our probability of being wrong if we reject the null hypothesis that we have equal variances, right? Now, we need that to be less than 0.05 to reject that idea and use the bottom row. Since this is greater than 0.05, our p-value for the test of equalities, we stick with the top row. Equal variances are assumed. So we can go straight across there, get our t-score, get our significance or our p-score, and so on and so forth, right? So this will give you the result that you need for that particular situation. Now, had the variances been more unequal, say one was more than twice what the other one does, well, presumably then SPSS might have given us a significance of less than 0.05, so we would have chosen to use the bottom line. Most of the time, it won't make a difference for you. Okay, most of the time, you can use either one of these two. Okay, but you should stick with the one that the test for equalities suggests that you should use. Okay, so another element of confusion to this, unfortunately, but it's manageable. All you have to do is remember that this has to be less than, you're going to stick with the top row unless this is less than 0.05. Then you're going to assume that the variances are not equal and you're going to use the bottom row instead. Okay, usually wind up with pretty close to the same t-value and significance p-value. So it's hard to go wrong with this, but you do want to stick with the right row that you wind up there, just for more for form than function probably. Okay, so now let's take a look at what's the next possibility here. The next possibility is if you have a situation where, let me go back to, we can't find that folder. There we go. Okay. The next possibility, if we have two sample t-tests and they happen to have unequal variances, right? The next shoe to drop. Oh, look, there's some old numbers there. Okay. Okay. So now this time, I'm going to calculate the standard. I wonder if I did this before. I guess I did. Let me recount. Let me get rid of those. I'll recalculate it. Okay, let's find the averages first. Okay, here's the average for this group. I guess they're the same as they're different numbers than before. This come out a little bit different. Okay, let's calculate standard deviations. Okay, let's calculate standard deviation. I'm going across here. Okay, so standard deviation here now. Oh, look at that. 1 versus 2.7. It's more than twice what the other is. So, I don't feel comfortable now saying necessarily that these have equal variances, because the variance 1 is almost 3 times the variance or standard deviation of the other, right? So what am I going to do in that situation? Let's go back to our table, a chart here, which tells us how to handle these situations. So in this case, the way we're going to solve this is that we're going to calculate our t-score. First, we're going to calculate our null and alternative hypothesis, of course. The mean for males is equal to the mean for females. Alternative hypothesis, the mean for males is not equal to mean for females, and so on and so forth. So now we're going to set our level of confidence, 0.05, 95%. Using the standard deviation, the means for each sample, now we're going to calculate the t-value. Okay, this is in the case where we're going to assume that the standard deviations are not equal. And when are you going to do that? When you do it mathematically, when one is more than twice the other. When you do it in SPSS, you're going to choose the line that Levine's test for inequalities is going to tell you to choose. Okay, so let's actually do this calculation now. Okay, again, I'm not going to do all the formal stuff. You really should. You need to write down your null and your alternative hypothesis and state your alpha, your acceptable level of error, and so on. But I'm going to go ahead and actually do this calculation. So the top part of this, the numerator, is going to be equal to 10 minus 7.5. The bottom part of this is going to be equal to, and I'm going to do this in two parts here. It's going to be equal to the standard deviation of this first one, equals the standard deviation here squared divided by the sample size, which is 9. Okay, I'm going to take that number, put it there. Then I'm going to take the second number, just so I can keep it straight. Standard deviation of this group times itself, divided by a sample size there, which was also 9, happened to be also 9. Okay, so now the bottom of this equation is equal to the square root of this plus this. Close this. It's equal to that. Okay, this is going to be bottom of my equation. And this is going to be the top of my equation. Okay, so my t-score is going to be equal to t x bar 1 minus x bar 2 divided by the square root of standard deviation of sample 1 squared over n1 plus standard deviation of sample 2 squared over n2 squared, which is this, and our t-score is equal to 2.5. Sounds promising so far, doesn't it? So the next thing I need is my degrees of freedom. Here's where things get a bit funky when we're talking about unequal variances. This is our formula for degrees of freedom. Pretty interesting, right? So a lot of people will say, I don't have like a week to work through this. And they'll just say, I'm going to take the sample size of the smaller group and use that as the degrees of freedom. So for instance, call it 9 degrees of freedom or something like that. That's probably not elegant. You can actually, if you hit the internet, you can probably go through some possible scenarios and what you might choose for that. Okay, so whatever that is, let's see what our t-scores are. Let me get a t-table. Okay, let's look at this t-table. Where is it? There it is over there. I'll pull this up here. Let's look at our t-table. 9 degrees of freedom. My t-score at 9 degrees of freedom would have my critical t is 2.26. Okay, so I'm going to get that out of the way. 2.26. Have I exceeded my critical value at t? Right? Have I exceeded 2.26? My critical value at t? Yes, I have. So what do I do with my null hypothesis? I know you guys are still there. Reject. Absolutely, right? And what is our p-value going to be when I do SPS when I use SPSS? What is my p-value going to be? Is it going to be more than 0.05 or less than 0.05? Since I know my t-score exceeds the critical value, what can I expect my p-value, my probability of being wrong to be? Going to be less than 0.05. Exactly right. Perfect. Okay, so let's give this a try. First of all, I want you to remember this nasty formula for degrees of freedom, because we're going to come up right now. Okay, so SPSS. Where is it? Where'd it go? There it is. Okay, and oops, that's not what I wanted to do. Okay, that's the output window. Okay, open, data. And now I'm going to get two samples, unequal variances. This is the one that we just did. And sure enough, I'm going to do analyze, compare means, except independent, still independent samples t-test, right? The values go in here. The grouping variables, male and female, go in here. And I define the groups as 1 and 2. Okay, continue. Notice this grouping variable is a nominal variable. And this values are a numerical variable. You find the mean, you're comparing the means by grouping them into two groups by gender. Okay, options I know is already set. Okay, let's see what I get now. Okay, so now, just as we did before, our t-score is 2.51, and our significance, as you would expect, is 0.023. Well, hang on a second. Let's go back here by this Levene's test for equality of variances. Levene's test for equality of variances. Let's see. My F-score, the score for that statistic is 7.8, whatever that is, whatever that means. But the value, the p-value is 0.01. At less than 0.05, I reject my null hypothesis that the variances are equal, and I assume that the variances are not equal, so I use my bottom row instead. Well, look at this. I'm getting slightly different answers here. I got the same t-score. My p-value is slightly different because I didn't use 16 as degrees of freedom. What did it use as degrees of freedom? It used a smaller number for degrees of freedom. I used 9, right? It used 10, right? In fact, it didn't use 10. It used 10.152 as the degrees of freedom. How did it get a weird number like that? Well, SPSS actually worked out that formula to calculate the exact degrees of freedom that it should be using in this case. Okay, so there we go. We've seen how to compare two groups using the t-score. Right, so we use this bottom one, and again, we reject the null hypothesis in either case because it's less than 0.05. Okay, let's see if there's anything else we need to know here. Do you want to just go over to the end here? I don't want to confuse you too much, at least not today. I'll confuse you another night. So I just wanted to point out to you that this 95% confidence interval of the difference, what this is the confidence interval for the difference between the two means. Mean of group A versus the mean of group B. If the two means are equal, you would expect the difference of the two means to be 0, right? So if you look over here in the confidence interval, if you see that the lower end and the upper end of your confidence interval contains 0, in other words, if this were minus 0.381 and plus 0.45, you would say, well, it could be 0. 0 could be between these two numbers. So you failed to reject the null hypothesis. Because 0 is excluded, what this demonstrates is you're 95% sure that the difference between the two means is different than 0. In this case, it's larger than 0, although we didn't predict that ahead of time. right? The difference, we're 95% sure the difference between the two means is not zero because both of these are higher than zero. The range is completely higher than zero for a confidence interval. Okay, just so you and you'll notice that that should almost always match your result with your t-score. Okay, so next, the last thing I wanted to go through for tonight, right? Well, this we introduce a lot of kind of complicated stuff. Is there's no reason why we can't apply this to proportions as well. Okay. Well, what kind of proportions might we apply this to? I wonder if I have an example of this here. I think I might have an Excel file. Paired samples. Oh, there was one other. Actually, I'm going to hold off on proportions. There's one other thing that I wanted to show you. Okay, and that is, I'm going to show you another Excel file. Okay, so now I'm going to take a situation where we're testing a drug and a placebo. Okay, now if this had been 9 people who took the placebo, and this had been 9 different people who took the placebo, what would we have here? We'd have a 2-sample t-test, independent sample t-test. But that's not what this study did. This study gave the patient number 2 the placebo for 6 weeks and the drug for 6 weeks and tested the patient. This patient took the placebo, got a 7. Then he took the drug, got a 5. This is the same person. These are results for the same person. So in a sense, what we're really interested in, well, what's the difference, for each patient when they were taking the placebo or taking the drug, taking the placebo, taking the drug. You also, a lot of these studies that do this kind of stuff, they randomize the order. This patient, number 3, might have taken the drug first and the placebo afterwards for a period of time, or this might have been the other. This might have been this first and this second, and so on and so forth. But this refers to one patient. So really, now we can remove a lot of variability. In other words, remember, if we took 9 random people, oh, maybe there were a couple of smokers in there. Maybe there are a couple of people who ate too much pizza. Maybe over here there are a couple of people that worked out all the time, right? That weren't over here. A lot of variability. So in a sense, we can remove a lot of variability by just looking at the difference in each subject. So I'm going to do that. I'm going to take the differences equals the difference between this subject, between when this subject was taking a placebo minus when he was taking a drug. No difference for that patient. So now I'm going to do it for all the other patients. Okay, so now the expectation is if the drug didn't do anything, the difference would be 0, right? So our test here is we want to know whether the difference, what's our null hypothesis? My null hypothesis is that the difference is equal to 0. My alternative hypothesis is that the difference is not equal to 0. Okay, I'm not predicting whether the drug is, I don't even know what this drug does. I'm not predicting if it's doing anything to help or hinder or whatever this number means, whatever it means, whether it's going to force it up, force it down, or help it go up or down or whatever. But I want to know whether if it made a difference at all. So my null hypothesis is that there's no difference. The difference is equal to 0 in this case. Okay, so now I'm going to find my average. My average difference. And my average difference is 1.55. Okay, you know what else I'm going to do here? I'm going to find my standard deviation of my differences. And the standard deviation of my differences is 2.69. So I got my mean difference. I got my standard deviation of my differences. And I got my sample size, which was 9. Okay, so now I want to compare whether this is different than 0. Okay, which is what I'm comparing it to. Oh, wait a second. This looks familiar, doesn't it? This is called a paired sample t-test. In a paired sample t-test, you only look at the differences for each subject. And you forget about the fact that there's actually two columns of numbers, really only the differences that you're interested in. And you're going to compare that to a set value. That value is 0. This is basically just a single sample t-test. So how do we do a single sample t-test? Well, we need to calculate standard error. What's standard error equal to? It's equal to it's equal to the standard deviation divided by the square root of the sample size, which is 3. Okay, it's equal to 0.89. So now what's my t-score? My t-score is going to be equal to the mean difference minus the number I'm comparing it to, which is 0, divided by my standard error. Okay, so what's it equal? What is t equal to? It's equal to this minus 0 over my standard error, which is this. So my t-value is 1.72. So you can see where this is going already, right? So since I have a sample size of 9, my number of degrees of freedom are 8. So if I go to my table, 8 degrees of freedom, we should remember that by now. I'm not going to bother to go over there. That's my t-value. My critical, t-critical, is 2.306, right? So have I exceeded my critical value for t? No. So what do I do about my null hypothesis and my alternative hypothesis? Fail to I like that. FTR, fail to reject. Very good. We're even learning shorthand now. Very good. I like that very much. So we failed to reject the null hypothesis. That's it. We don't say we accept the null hypothesis. We don't make any predictions about it. We just say we failed to reject. Now, I think you can probably just do the same thing with this in SPSS. And if we're really lucky tonight, we will have gone through the whole night getting the same, basically, not exactly, basically the same answers in SPSS and Excel as we did all these calculations. Paired samples. Okay, and now I'm going to go to Analyze, Compare Means, Paired Samples t-test. And it's going to come up and it's going to wait for me. Oh, I have to, because these numbers are small, sometimes it thinks they're categorical variables. So I gotta straighten it out. They're numerical variables, scalar variables. Okay, let's go back. Okay, so now I'm going to go Analyze, Compare Means, Paired samples t-test. I made these simple numbers so that the numbers didn't get in the way of our understanding of this. Okay, in a second, I'm going to do a real demonstration of this. Okay, so I'm going to move in. What are the paired variables? Well, one is when the person was taking the placebo, and the other one was the person taking the drug. Notice the OK thing didn't light up until I had paired two variables. Options 95%, so 5% chance of being wrong. Alpha is equal to 5%. So let's go do our analysis. Our output window pops up. Here we go. And let's see what our result was. Okay, our result was that let's see, placebo average was 10, 8.44. They got a different average than I did, didn't I? Oh, no. Okay, maybe I'm wrong. Maybe, I don't know. Sometimes I change these numbers. I'm never sure about why. Sometimes when I demo stuff, I'll change numbers, then I save the file, and I forget to put it back the way it was. But okay, but at any rate, we got the same result in the long term. Okay, our mean difference was 1.55. Our standard deviation for the differences was 2.698. Our standard error was 0.89. Remember, divide this by the square root of 3, right? And our t-score was 1.75. So that should mean 8 degrees of freedom, right? Because the sample size is 9. So that should mean that our significance, our p-value, is greater than 0.05, more than 5% chance of being wrong. And indeed, there's our p-value, our probability of being wrong, probability that we would get this outcome if the two means were the same, we would get it 12% of the time, not less than 5%. So in other words, we could be wrong 12% of the time if we rejected the null hypothesis now. So our t-score is less than the critical value, and our p-value goes along with that. It's greater than our acceptable level of error, which is 5%. Okay, I'm going to hold off on proportions because this has worked out pretty well so far. I'm going to maybe do that on Wednesday. And I'm going to have to review a bit of this because a lot of people weren't here for this. And I'm not so sure that I'm going to be able to get these link to them. We just, you guys that have logged in since we started, we checked out Blackboard and it still wasn't up yet, which I think I kind of predicted. I don't want to say I told you so, but I told you so. So at any rate, I just want to show you one other example of this, maybe something that's a little bit more real life. Okay, and I'm going to go to SPSS. Yeah, so this kind of, when they do this, these upgrades, while we're still working, it really kind of screws things up. Let's see. Open, data. And I'm going to go to a data set that I think we have used at least once so far. I'm going to open this data set. Yeah, don't worry about the formatting. Okay, let's take a look at this. Okay, so one of the things I'm interested in here is, let's see if there's a numerical variable here. Well, the mother's age is a numerical variable. Well, the amount of weight that the mother gained during pregnancy. Okay, so I am curious to see that if a mother smoked during pregnancy, whether she gained a different, if the average amount of weight that a mother gained during pregnancy was different for mothers that smoked versus mothers that didn't smoke. That's a t-test. I'm looking to see if the average for mothers who smoked is different than mothers who didn't smoke, right? So I'm going to go to Analyze. I'm going to go to Compare Means. Those are independent samples now, right? Randomly sampled mothers, and some of them were smokers, some of them were not. Okay, so now the test variable is the weight gained during pregnancy. That's what I'm taking the average of. The grouping variable is the smoking status of the mother. Now, again, I got to define the groups. I'm going to have to guess. I'm going to guess it's 1 and 2. I should have looked this up before I should have gone to the data view and looked it up. Okay, and the options, I want to make sure this is 95% if we're using, so now if we go through our steps, null hypothesis is that there's no difference in the mean weight gained for smoking women versus non-smoking women. Alternative hypothesis, there is a difference in the mean weight between smoking mothers and the weight gain in smoking mothers and non-smoking mothers. So I'm going to click OK. Alpha is equal to 0.05. And things messed up here because it couldn't figure it out because I gave it the wrong numbers. Analyze, compare means, independent samples t-test. I'll bet you this was one instead of 0 and 1, 1 and 2 was 0 and 1. I could actually go in. If it doesn't work now, I'll actually do what I should have done, which is actually go back there and do it. It worked this time. Okay, that's what it must have been. Okay, oh, it's up now. Excellent. Okay, good. I'll be able to post this then. Okay, so let's see. Number of mothers who did not smoke, 64. Number of mothers who did smoke was 113. The mean was 30.65, 30.19. Not a big difference in mean weight gain, right? Interesting. The variability was very similar. So chances are Levine's test is going to say to assume equal variances. And the standard error was a bit different. Oh, you know why the standard error is so different? Because of the difference in sample size. Remember, it's the standard deviation divided by the square root of the sample size. Look how many more mothers didn't smoke versus who did smoke. So it'll be interesting to see how SPSS resolves that in calculating whether or not we should assume equal variances or not, because that's so different. Let's take a look. Well, in fact, SPSS, Levine's test says, well, its significance is less than 0.05. So we should use the bottom line, not the top line. Okay, not going to make much difference because look at this. The t-value is 0.294, right? We know that's pretty, no matter what you do, that's pretty small t-value. And the significance, is it less than 0.05? No, it's 0.769, right? So because the t-value is so tiny and the significance, the p-value is so large, we fail to reject the null hypothesis. So we don't have the evidence to demonstrate as you probably would have guessed when you saw these two means, we don't have the evidence to demonstrate that that there is a difference between the mean weight gained for these two mothers. It's a little bit before 7:30 still. Let me just do one more. Analyze, compare means, independent samples t-test. This time, let's compare the weight of the child at birth on smoking status. Let's get that one. See what we got this time. Oh, wow, look at this. Okay, now, now if we're going to use the top line because equal variances. This is not less than 0.05. This time, the mean weight of a child born to mothers who did not smoke was 117 ounces, and mothers who did smoke was 109. So this time, our null hypothesis is no difference in the birth weight of the baby, mothers who smoked versus didn't smoke in this study, right? And the t-score is 3.51. Degrees of freedom is 796, right? It was 800. It was sample size was 798 minus 2 is 796. Okay, and the significance is tiny. It's less than 0.001. When you see 0.000, it's not really zero. It means it's less than 0.01, 0.001. So in this case, we reject our null hypothesis that the mean weight of infants, the birth weight of infants from mothers who smoked is equal to the mean weight of infants of mothers who did not smoke, and accept our alternative hypothesis that the mean weight for mothers who smoke is different than the mean weight of infants from mothers who didn't smoke. Okay, so at any rate, so you guys got an idea. This is when you work now with two groups and you're comparing them based on a numerical variable. This is where you're going to be using in the future. And for the most part, you're going to be using SPSS to organize your data, or some similar program to organize your data to evaluate it, to describe it, to do descriptive statistics, and then to do your statistical test. Set up your hypothesis test and do your statistical test to see if you can reject your null hypothesis and prove what you're trying to prove at the level of confidence that you want. Okay, so I hope that was clear. I think it's somewhat of an exercise to get you started. So what I'm going to do is I'm going to post homework number 4, which will start to ease you into this stuff. If I can get onto Blackboard, I understand Blackboard's up now. So if I can get onto Blackboard myself, and it's working, I'll start, the next day or so, I'll post on like number 4. And then I'll see you guys, today's Monday. Have a great 4th of July. Okay, don't play with fireworks. Right? Your public health people do not play with fireworks. And then on Tuesday, I as a kid, I was injured with fireworks. Not a little minor injury, but I'll tell you a cute story. I was hanging out with some drunk relatives when I was about maybe 10 years old, 10 or 11 years old, and I was having a great time watching them throw what they used to call back in those days ash cans. They're not M80s, they're smaller. They're kind of like little tubes with a few comes out in the middle, and they had these little wood or plastic ends and pushed into the tube to hold the gunpowder in. And I was having a great time watching these two drunk idiots throw it at each other. And one of them took a bad bounce and wound up behind me. And I heard a bang, and I felt a little tug on my pants. And you guys that have worked in emergency rooms are gonna appreciate this. So I didn't think too much of it. But then I looked down and I was bleeding. There was a little hole in my pants and I was bleeding. And one of those the little end caps was to come out and clip me, kind of like a little bit of shrapnel, and got me in the leg. So they took me to the emergency room. Of course, they're loaded, and I'm a kid, so they sent me into the emergency room. And I go up to the doctor, the emergency room, daycare, Johnson. You can leave if you don't want to hear the story. You're not required. It's not a required kind of story. So at any rate, the doctor treats it, dresses it, and so on and so forth. And he says, "How'd you get this?" So I told him, being a 11-year-old kid, I told him, I got it climbing a fence. So the last words he said to me as he was sending me off was, "Well, pretty interesting. That fence gave you powder burns, right?" So if you're an 11-year-old kid and you're working in the emergency room on July 4th, you're pretty much going to be caught. So have a great 4th of July, guys, and I'll see you guys on Wednesday night. Bye.